Hello, this is Scott Socolofsky at Texas A&M University, and I'm presenting here what we call Module 2, which is part of a short course that was originally presented at CTAC in 2016 in Orlando. This module is an overview of oil phase transfer and transformation processes. So the subtitle, Oil in the Aquatic Environment, Sources, Fate, Effects, Monitoring, and Response, is the overall course title. In this module, we'll be talking about how oil moves through the environment, in particular how it is transformed as it does so. These slides were not created in a vacuum by myself, so at the bottom I'd like to point out the contributors who reviewed the slides, gave me comments, and helped to improve the slides, both Chris Barker, who's at NOAA Response and Restoration, and Court Cooper, who was formerly at Chevron and is now retired. The outline for this presentation, I'm going to start with an introduction to what we mean by oil phase processes, and then I'm going to give some examples of how these were in action during the Deepwater Horizon spill. After that, we're going to go deeper into how we describe these processes for modeling. So we'll start with an introduction to the properties of oil that are involved in calculations of oil phase, discuss the gas-to-oil ratio, and then we'll look at a series of processes, first in the subsurface as we form droplets. In the deep water, perhaps a gas hydrate could form on the bubbles and droplets. We'll have chemical mass transfer, which is dissolution, biological fate, which is biodegradation. Then after the oil gets to the surface, there are other processes that can start to be added to these, such as wind, which is going to cause mixing and turbulence. Evaporation into the atmosphere is also going to change the properties of the oil in a process we call weathering. The sunlight can degrade different compounds of the oil in photodegradation, and then all the action of this evaporation, the wind, and turbulence can form emulsions, which are water and oil stable, or not necessarily always stable, but mixtures. Finally, we'll touch on a few other things that might happen at the sediment-water interface and then try to summarize this presentation. So starting off with fate, what do we mean by oil transport and fate? Here's a schematic diagram of a kind of cartoon picture of a deep water oil release, oil spill. We have oil and gas coming out of the sea floor, rising up through the water column, being deflected downstream by currents. So we can see on the left here that currents are higher in the upper water column than they are in the lower water column. This bends over the plume. We also have density stratification. We have colder, higher saline water, usually in the deep water, which is denser than the warmer, perhaps lower saline water in the overlying ocean, so that we have a density profile. As this plume of oil and gas tries to lift the water that gets entrained into it up higher, this density profile is going to prevent it from lifting that all the way to the surface, and we can form a subsurface intrusion layer. This looks a lot like what you'll see above a chimney plume, say above a power plant or any kind of chemical plant, where you can see these formations of these clouds downstream in the atmosphere. And this is also what happened during Deepwater Horizon in this well-known subsurface plume or intrusion. It has a characteristic height, a trap height, and it's going to be highly diluted by all of the water that's been sucked into this plume on its rise through the water column. The gas bubbles and the large oil droplets may not be able to be pulled down into this layer, so they'll continue to rise. Maybe they form another plume as shown here. If the currents are strong enough and spread them out over a big enough area, then they would not. And they would rise to the surface where they have surface processes, and then the oil in small droplets that goes into this subsurface intrusion is mostly dissolved compounds and then very small droplets that are wafted down by the ocean current. So the kinds of fate processes that are happening here and the things that control them, at the seafloor on the left-hand side, we list the important initial conditions. So the flow rate of oil and gas coming out of the spill, is critical to knowing the volume entering the water column. Then the size that is pouring through and the turbulence generated there is eventually going to give us some bubble and droplet size distribution. And then the density of this oil and gas is going to give rise to the force that pushes it up through the water column. It's usually the gas for sure is lighter than seawater. The oil is somewhat lighter than seawater, and so it's going to push up through the water column. The things that are going to affect the mass transfer or dissolution or the state in the water column is that in very deep water, natural gas hydrates may form. We'll talk about those. There's the crystalline matrix of natural gas and seawater that could interfere with the dissolution of what's inside that shell. The gas and oil themselves are complex mixtures, so it's not so simple as pure methane dissolving into the seawater, but it's methane in a mixture of ethane, propane, and lots of other hydrocarbons. And so that gives rise to a non-ideal gas behavior of the gas and a non-ideal mixture behavior of the oil. Both the gas and the oil will dissolve, but at different amounts. The oil, usually in the reservoir, is at much higher pressure. It has a lot of gas dissolved into it, and so this gas starts to come out of the liquid phase solution in a kind of effervescing or what we call evolution effect. And then, as I mentioned before, with the high turbulence, both in the plume and then later its pre-surface, we may form emulsions. Emulsions are like what you see in your salad dressing. If you take it out of the refrigerator, it's separated into oil and water. When you shake it up, it stays as a mixture for some short time. And depending on the properties of the oil and the amount of turbulence involved, you can form emulsions that are not very stable, like your salad dressing. It will separate out in a few minutes or an hour. Or very stable, like petroleum jelly is an emulsion that is highly stable and can last for years. So what does this look like? Here's a picture of the Deepwater Horizon after they cut the riser and before they installed the top hat. You see that it's that the oil and gas is coming out together in a mixture. It's breaking up into small bubbles and droplets, and it's forming a buoyant plume. Plume is what we call this turbulent structure that is narrow and rising up through the water column. After that oil eventually makes it to the free surface, the ocean currents and the winds move it around, and it can form a very complex structure in the environment. This is a satellite image of the Deepwater Horizon on a particular day, and you can see a lot of the fine-scale structures of the different thicknesses of oil slicks that are now on the free surface. So we've already looked at the cartoon of the idea of a subsurface plume or intrusion. Here are some data from the Deepwater Horizon. On the left, what we see is a profile of a CTD, a conductivity, temperature, and depth probe that we lower through the water column. And in blue, we see the decreasing temperature, and in black, we see the increasing, this is oxygen, I think. It's not labeled well. This is salinity. So black, we see the increasing salinity. But the thing to focus on here is the fluorescence profile. So I think in this case, when the wet lab fluorometer was on the CCD, and when it encounters oil can fluoresce at a certain excitation frequency. So think of a black light on fluorescent markers. This is the same idea. The light from the fluorometer causes oil that's present in the water column to fluoresce. You see a very large peak here at around 1,200 meters depth. The discharge was at 1,500 meters. So the plume rises up through the water column and then forms this subsurface layer that has a lot of petroleum compounds in it. In this fluorometer profile, it also looks like there may be a small intrusion a little higher in the water column, and when we compare this single measurement to a paper published by Terry Hazen's group, Spear et al., Environmental Pollution, Volume 173, they looked at many CTD profiles collected throughout the spill and then showed the abundance of different types of petroleum compounds in the water column. And we see this big peak at 1,200 meters, which is the main subsurface intrusion, another peak about 900 meters, and then the surface slick, and then some other peaks associated probably with the thermocline or the pycnocline of the density stratification. After the oil made it to the free surface, then it begins to evaporate into the atmosphere. And one other very important measurement taken during the Deepwater Horizon was by Ryerson and his group from, I believe, USGS, and they flew airplanes through the atmospheric plume rising up from these evaporating hydrocarbons, and they measured different compounds. You can see them listed down here on the bottom in the atmosphere. So on the left-hand side, we see the fraction that are in the atmosphere, and these are the open symbols. And so for methane, they measured virtually none. Ethane, also almost none. Propane, the line goes up slightly. As we move to the right, the hydrocarbon chains are getting increasingly longer, and we see that more and more of those compounds are measured in the atmosphere. So these red open symbols are the measurements in the atmosphere. Then the solid symbols show the fraction, therefore, that must be dissolved subsurface because it didn't go into the atmosphere. So 100% of the methane must have been dissolved in the ocean water column, much of the ethane and propane, benzene, and as we move down into larger molecules, for instance, toluene here, we see about 70% dissolved in the water column, and then once we get up here to these longer, here's heptane, it's almost entirely makes it to the surface and not dissolved in the water column. These are compared to the profile of what came out of the wellhead. The lower graph just compares what was measured in the atmosphere to what came out of the wellhead. So certainly a lot of methane came out of the wellhead and none of it was measured in the atmosphere. So we can see that once we get to these longer hydrocarbons, then what came out is what was measured to make it to the free surface. Okay, so how are we going to predict during a future spill, or if we want to hindcast the Deepwater Horizon, say for natural resource damage assessment, how do we predict graphs like this where we want to know ahead of time how much of the released fluids are going to be dissolved in the water column, how much of them are going to be released to the atmosphere, where are they going to insert themselves into the water column? We need a model to describe the oil and its chemistry, and then ways to track it through the water column. So when we think about the oil coming out of the C4 or down in the reservoir, or eventually in a production situation in a tanker, oil is comprised of a liquid phase and a gas phase, and there will, at any certain temperature and pressure, these will be in could be in an equilibrium, and there we would have a mixture of that oil in gas and the same mixture in a liquid phase. Usually we call the gas gas and the liquid oil, but really all of them contain the same compounds of petroleum molecules. So the gas is going to be predominantly, say, methane, but it will also have very long-chain hydrocarbons dissolved into it, just at very low concentrations, given the vapor pressure at the gas-liquid interface. So the types of properties we might need to know about these two fluids is their density and their viscosity. The density controls how fast they might rise through the water column. The viscosity controls how turbulence can cause them to break into smaller particles or mix with the water. The surface tension, interfacial surface tension will help control what size oil droplets and gas bubbles can be formed. Lower surface tension will form smaller droplets than a higher surface tension. Once it starts to dissolve, then the thermodynamic diffusivity, the molecular diffusivity of each compound in water, is going to be a rate-limiting step for their dissolution. And then their solubility is the driving chemical potential. So the higher the solubility, the more there is a thermodynamic force trying to push it from the petroleum mixture of oil and gas into the dissolved water. But the diffusivity, how fast those molecules will diffuse into the water, is still the rate-limiting step that is going to happen at the oil-water interface. And we'll be looking at models of this here shortly. And then the way we describe these is by some sort of fraction of each compound, either a mass fraction or a mole fraction of each compound. Say methane, maybe 30% in the gas phase and 70% in the liquid phase at a high pressure in temperature, and at lower pressures it may be 99% in the gas phase and 1% in the liquid phase. So those are the types of properties we will use to describe these fluids. As they then move through the water column, they're going to change their composition. So the complicated thing is that oil, petroleum fluids contain a very large number of individual compounds, tens of thousands of compounds. And each oil coming out of a different reservoir will have a different fraction of each of these compounds in its mixture. So all oils, in a sense, are unique. Now, some oils have similarities with each other. There are sweet oils that contain very low sulfur. There are sour oils that have more sulfur. There are light oils that contain a lot of lighter hydrocarbons. There are heavier oils that contain fewer of those. But in every reservoir, the actual mixture is different. And the way these compounds interact with each other give rise to different properties. They'll have different density, different surface tension, different viscosity. The way we can predict those is through an equation of state. And these equations of state try to predict their physical properties, such as density, viscosity, surface tension, interfacial tension, and their chemical properties, which is their solubility, their composition at equilibrium. So as the gas and oil move through this aquatic environment, they're going to dissolve, which is going to change their fraction. So if the methane leaves the gas, then it will no longer contain methane. That will then change the gas's density and potentially its interfacial tension. So models we build to predict the fate of oil in the water column have to keep track of how the composition is changing and how that changing composition then affects the properties. So equations of state are very important for this. There are different options that we can use. The more complicated, not as complicated as possible, but one of the more complicated methods is the Peng-Robinson equation of state, which I'll talk a little more about in a moment, where we try to write down as best we can the components in this mixture and then track their properties and how they influence the oil and gas properties. But we can also have very simple equations of state, such as a simple compressibility equation that says if the pressure is released by this much, then the density changes by a proportional amount. So there's a wide range of complexity we can put into the equations of state. And choosing the right equation of state sometimes will depend on the amount of information you have. So if you have a lot of information, for instance, you want to use the Peng-Robinson equation of state to predict the density of a gas mixture, then you need to know the fraction of methane, ethane, butane, decane, etc. that are in the gas phase. And if you use the actual compounds themselves, such as N-butane, which is a particular molecule, then that has the advantage that we know we can look up in tables what their actual properties are, say their critical point temperature, critical point pressure, boiling point, etc. And those may be tabulated in thermodynamic tables. But once we get past first 20 or so molecules, as you go down the number of the length of molecule, then they start to have lots of variants of how these molecules can look, and it becomes almost impossible to have an exhaustive list of every molecule present in the mixture. So instead, what we do is we start to group similar molecules together into so-called pseudo-components, and a pseudo-component is just a component we put in the model that represents many different compounds in the oil. So one example would be a C16 alkane. Alkanes, C16 can have multiple different shapes, and so if we group together, in this case C16 alkanes, we're putting all compounds like that into one group. But you can make bigger pseudo-components that could be C16 to C20 alkanes. And then what you need to know is the mass fraction of that group of compounds in your oil. Sometimes we get that from a boiling profile. And then you have to estimate what the properties are of those compounds in that group. And this becomes a little more complicated because you can't generally look those up in a thermodynamic properties table, because in a given oil, what is in this pseudo-component that I choose may be different. So C15 to C16 alkanes could be different in one oil than it is in another, and because it has a different set of compounds with a different ratio, then it will have different properties, a different boiling point, for instance. So pseudo-components are nice in that I can use fewer compounds to describe my oil, and I don't need 1,000 or 10,000 compounds, but they're not so nice in that now each oil has slightly different properties. Now, especially the smaller ones, and if we're in a certain branch of oil, like Louisiana sweet crude somewhere in the Gulf of Mexico, it may have similar properties from reservoir to reservoir, but in essence, every oil will have a different set of properties for its pseudo-components. Many oils have been tabulated and are available in online databases, and we can use those databases if we know we're dealing with a known oil to try to build this composition. So when we think about gas-oil ratio, I want to start off by looking at soda coming out of a soda can. We know CO2 is dissolved in the liquid. We've just opened this can, starting to pour out. Initially, there were almost no gas bubbles. Now, as the pressure has been released for longer, the gas starts to come out of solution, forming bubbles. And the same thing is happening in an oil as it comes from the reservoir, which is at high pressure with lots of gas dissolved in the liquid phase, and it comes up the pipeline eventually to the production rig where the pressure is much lower. That gas is going to come out of solution. And in the oil spill, when the oil spills out of the wellhead, it will be in some state of evolution towards this equilibrium. And the way we describe the amount of gas that's dissolved in the oil is through the gas-to-oil ratio. So the gas-to-oil ratio tries to tell us the amount of gas in the reservoir compared to the amount of oil, and usually this is specified once the oil comes up to a production facility and has fully equilibrated with the atmosphere. So we would then state the gas-to-oil ratio as the amount, the standard cubic feet of gas that would come out of a given unit of oil, and the number of stock barrels of oil you would get at the same time. This tells you the end composition, but it does not tell you the composition in the reservoir, nor would it tell you the composition when it came out of a spill, such as the Deepwater Horizon at 1,500 meters depth. So this composition, the amount of gas to oil at equilibrium, will vary with temperature and pressure. So during a spill scenario, this equilibrium is not instantaneous, and it varies through the water column. So here's a good example for Deepwater Horizon. The measured gas-to-oil ratio ranged between 1,600 to 2,200 standard cubic feet of gas per barrel of oil. So once that fluid was produced, say, to a rig, it had a whole lot more gas per unit volume than it had liquid. But at the wellhead, where it was coming out at 1,500 meters depth, if we do an equilibrium calculation, about 40% of the volume coming out at equilibrium would be in the gas phase and 60% would be in the liquid phase. This has two implications. One is that it changes the flow rate. So when we say 50,000 barrels per day of oil was spilled from the Deepwater Horizon, we're talking about stock barrels at atmospheric conditions, but the actual volume flow rate at the seafloor would be different because it has a lot of gas dissolved into it. Actually, the volume flow rate would be more than 50,000 barrels by volume of liquid phase coming out. It also changes the density that having all that gas dissolved into it. So the Deepwater Horizon oil produced at the surface from one citation early during the spill said it would be 840 kilograms per cubic meter. When we do an equilibrium calculation and find out that 60% of the volume is in the liquid phase, that liquid phase has a density of 650 kilograms per cubic meter because there is a lot of gas dissolved in there, making it lighter. So the next step, once we have a model that can help us to predict the properties of oil and gas and their separation, then we have, if we're modeling a spill or understanding the fate of oil in the water column, we then have to have a spill and predict the sizes of the droplets in the gas bubbles before we can say their fate. So on the first video here, we see a laboratory experiment of a release of oil droplets with no dispersant added. We'll talk about dispersant in a minute. You may remember during Deepwater Horizon that a chemical dispersant was injected at the wellhead to help promote smaller droplets. So here's an example with no dispersant. When we run the exact same experiment, but we add chemical dispersant, you can tell by looking that it looks much more milky. We don't see big droplets coming off anymore. We really can't see any individual droplets anymore, and it has a different size distribution. At the very end of this experiment, at the top, you see some large droplets. At the end of this experiment, you see that those large droplets are not present. So by adding chemical dispersant, it's the name of the compound dispersant itself tells you what it does. It helps to disperse the oil by breaking it into smaller droplets. Whether or not that is injected at the wellhead will affect what the droplet size distribution is coming out. So to predict the fate of oil, especially its transport, how fast it rises and where it goes, one of the most important things to predict is the size of the oil droplets. Smaller droplets will rise much slower than larger droplets. And so we have to know what the size is to know where they will go. Since Deepwater Horizon, we have made a lot of progress through laboratory experiments and modeling to build models that are capable of predicting this for spills like Deepwater Horizon. Of course, future spills may be of a different character. We usually describe the droplet size by some value. In this case, this is the median size of a droplet, where 50% of the mass of the oil would be in smaller droplets than this size. And we know that it's going to depend on several things. It will depend on the size of the hole that the oil is flowing out of, depends on the velocity that the oil is being emitted, the density of that oil, because that gives rise to its buoyancy, the density of the receiving water, because as that water is entrained in, it changes the amount of momentum, and it also starts to create the turbulence that breaks these apart. So the velocity of the exit and the density of the ambient receiving water all together give rise to some turbulence that are going to break up this oil into smaller droplets. Then the viscosity of the oil is going to try to resist the breakup into small sizes, and the interfacial tension is also going to resist the breakup. When we add a dispersant, we are trying to change the interfacial tension, but it doesn't have much effect on viscosity. But the interfacial tension is the dominant property that's resisting breakup for the oil droplets when they're released. We know that oil and water don't mix directly, and that the interfacial tension is showing us that if we can make it small, we can get them to mix better. So here's a picture of what a predicted oil droplet distribution might look like. We have this one characteristic value that we're trying to predict, we call D50, and then this distribution also has a spread. Based on early experiments, it looks like the spread of the distribution, the width or the standard deviation, is fairly constant from experiment to experiment. Recent data shows that it might be a little more variable, but currently I don't know of any models to predict this as a function of different oil or release properties. It's basically assumed, or we run a different type of model. Here I'm talking about a very simple empirical model to predict droplet size. We can predict the standard deviation using population dynamics models, which try to model the breakup process on a droplet by droplet basis. Here I'm just talking about simple empirical equations to predict these sizes. So here we can see the effect of flow rate. If I increase the flow rate, so I have a higher exit velocity, I'll get smaller droplets. So the dark ones have a higher exit velocity, smaller droplets than the larger ones. Droplet size is on the x-axis. If I change the, let's see, volume. Oh yeah, this one again, I'm reducing the volume flow rate, and so I have larger droplets at the lower flow rate, and it's fairly similar. If I make the nozzle smaller, then it will have a higher velocity coming out of the nozzle, so the same flow rate can generate smaller droplets. So these graphs all indicate the fact that the exit velocity is an important parameter controlling the droplet size. This shows the effectiveness of dispersant injection. If we also inject dispersant right where the oil is coming out of a nozzle, then these three sets of data have exactly the same exit conditions, same flow rate, and same nozzle diameter, but have different amounts of dispersant. So in black, there is no dispersant. Median size is somewhere around 200 microns. When we add a little dispersant, 1 to 50 volume ratio of dispersant to oil, we can reduce that droplet size by about a factor of 2 to somewhere around 100. And when we add 1 to 25 dispersant, we can drop it almost a factor of 10 from 200 down, say, 50. And notice this is a log scale here on the x-axis. So by adding dispersant, we change the interfacial tension, we're able to reduce the droplet size. So as I said before, smaller droplets take longer to rise to the surface. So here, this is an example of what could happen to, say, a deepwater horizon oil droplet. If I take a 29-degree API, that's a way of stating the density, droplet, and release it at 1,500 meters depth, and the diameter of the droplet is 1 centimeter, it will rise to the water surface in a matter of about 3 hours. So this is a log scale on hours on the y-axis. If I make that same droplet 10 times smaller, so now it's 1 millimeter in diameter, instead of 3 hours, it takes close to 20 hours to rise to the free surface, and then droplets that are another order of magnitude, so 0.1 millimeters, take over 1,000 hours to rise to the free surface. During that rising time, it has more time to dissolve into the water column, and also the lateral currents in the ocean can push it further downstream. Okay, so now let's look at the phase processes that can happen for these individual gas bubbles and oil droplets after they're formed at the release and start moving through the water column. So the first thing we're going to discuss is what I mentioned earlier, this idea of hydrates. Hydrates are a crystalline matrix of certain gases and water. So methane, ethane, and propane all form hydrates with water at different temperature and pressure. Here is a chunk of methane hydrate after it's been recovered from the seafloor and brought up to the surface on a ship and then lit on fire. You can see it burning there. Here is a picture of a methane hydrate crystal coating a methane gas bubble in a laboratory experiment at high temperature and low pressure. This crystal is just a thin, ice-like case around the gas bubble. So we might assume that this crystal structure could change the rate at which methane gas would dissolve into the water column. So now we need to start talking about how do things dissolve out of either an oil droplet or a gas bubble. So this is kind of a complicated looking figure, but I'll break it down to you. Let's consider this to be an oil droplet. It's going to rise up through the water column based on its being a lot less dense than the surrounding water. As it rises, it's going to be dissolving the lighter compounds into the surrounding seawater, and there's going to be a buffer layer here where we have basically the solubility limit at the oil-water interface. So right here, it's next to the oil, the concentration is going to be the solubility of that compound in water. But then not very far away in the seawater will be some lower concentration usually. And this buffer layer we call it the concentration boundary layer, and the thickness of that layer is going to tell me how fast oil might dissolve out. The thicker this layer is, then the lower the potential. It's basically surrounding this by water that's already saturated. If I make this layer very thin, like up at the top, then it might dissolve quicker because I don't have very much saturated water nearby. So how do I predict how fast things are going to dissolve out or even dissolve in? We use an equation like this that says the change in the mass as a function of time is equal to the surface area over which this mass transfer is happening, a rate constant of how fast it can dissolve out, and then the chemical potential that tells you what the solubility is and what the ambient concentration is. So the bigger this chemical difference, so if something's very soluble and not currently present in the water column, we have a big difference in concentration, we can have a much faster mass transfer. If something is already either not very soluble or already present in the water column near solubility limit, then this potential is lower and it won't be dissolving anymore. So this mass transfer coefficient is what's capturing this light blue boundary layer effect and the rise velocity and complicated turbulent wake behind this bubble. And so this mass transfer coefficient tries to summarize the effects of the chemical boundary layer and keeps in mind the fact that molecular diffusivity at the gas-water interface is the rate-limiting step. For gas to get out, it has to overcome molecular diffusion rates in water at the gas-water interface because there isn't any turbulence right there touching the gas bubble. Okay, once the bubble or droplet has been rising through the water column for a long time, it may start to be colonized by bacteria. Here I'm showing an example of an oil droplet that has been coated by a biofilm. And there are basically two models available in the literature to try to predict how this might be behaving. In the one model, it says that the bacteria are going to reduce the hydrocarbon mass just by first-order decay. And here we don't need to know the droplet size, we don't need to know the surface area, we just need to know the concentration of the oil in the water and the rate that the bacteria are attacking that oil. And this gives rise to exponential first-order decay. The other model says, well, the biofilm is on the outside and the oil is being eaten from a layer that has a certain surface area, and it's going to disappear in proportion to the surface area. So these would be droplet size dependent models, and this other one would be independent of the droplet size. There's not a lot of data yet for liquid oil droplets that help us to choose the correct form of these models. So for now, we're basically looking at both of them as hypotheses of how this process may be occurring. In the first model, I think it's fairly safe to say that the oil has to dissolve into the water phase before it can be biodegraded, because if it's actually degrading the liquid oil itself, then the surface layer and the collection of this biofilm has to occur. And probably in reality there's some combination of both. There are going to be dissolved hydrocarbons in the subsurface layer, and the bacteria suspended throughout that water are going to be decaying it, following this rate law. At the same time, any oil droplets present in that layer are going to be colonized by oil and may be degraded by this law. So then, looking as this oil rises through the water column, the gas that's dissolved in the oil may start to come out of solution, just like we saw the gas bubbles coming out of the soda can. And we don't have very good information of how this might occur. It may be that some large gas bubble forms, or it may be that lots of little tiny gas bubbles form, and then these could quickly dissolve away. We don't really know. And if it's one or the other, it's going to depend, it's going to change the density. If the gas comes out of solution and stays stuck on this oil droplet, then it's going to have a much lower net density and rise faster than if lots of little tiny oil gas bubbles form that rapidly dissolve or escape out into the water column, so that the density stays closer to the oil density. So dissolution, we've already looked at the model. The cartoon picture is that we have a boundary layer trying to reduce the dissolution. We have a mass transfer that is in something that's dissolving, has that compound moving out of the mixture of oil into the water phase. So we've kind of talked about the different processes. What we're doing here is we're looking at, I think I've already discussed this slide, just saying that which one of these processes occur depends on what is being degraded. Most likely, it's dissolved hydrocarbon that's being degraded from the water, and liquid hydrocarbon being degraded from the surface of the droplet. After these droplets and bubbles make it eventually to the free surface, then depending on how well they are spread out, they may form slicks and then undergo new processes. So let's think of Deepwater Horizon, and before we injected subsea chemical dispersant, a lot of oil was coming relatively quickly to the surface, relatively close to the oil well, and formed slicks that, because in order to form a slick, you have to have enough oil coming up at the same place that it can start to get together and form slicks of different thicknesses. But once they started injecting chemical dispersant, the purpose of doing that was twofold: make smaller droplets that will spend more time in the water column so that they will have less mass making it to the surface, because the longer you spend in the water column, the more dissolution, the more biodegradation can occur. But then the other effect, the other reason, the second reason, is to make smaller droplets that will be transported much farther downstream. The farther they go downstream, the more natural turbulent diffusion can spread them out. And so it's possible with subsea chemical dispersant addition that you could prevent the formation of surface slicks. In fact, that's one thing you're trying to do. And here I should mention that, well, I'm getting a little bit ahead of myself. So now let's imagine that we have a situation where a surface slick of some thickness has formed. What processes are going to be happening at the surface? Well, instead of dissolution, which is coming out of the droplet or gas phase into the water, we'll have evaporation. It's going to come out of this surface liquid oil and go into the atmosphere. Evaporation depends on the vapor pressure and the wind speed. The wind is generating turbulence in the atmosphere to help move the evaporated fluids away. At the same time, sunlight is now coming in contact with the oil, and the sunlight, the UV rays, are absorbed by different molecules in the oil, and some of these molecules are going to be transformed in that process through a process called photodegradation. So the oil might be changing its chemical composition just by interaction with sunlight. The wind is going to be kicking up surface waves. These surface waves may, if they're strong enough, plunge down into this surface slick and then pull the oil droplets down into the upper layer of the ocean. Depending on the amount of turbulence available, you may be able to form emulsions, which are stable oil in water mixtures or temporary oil and water mixtures. And then the oil droplets that are suspended in the water column here near the surface are going to be undergoing dissolution, although maybe a lot of the dissolution has already occurred, and biodegradation. So when we use chemical dispersant subsea, we're trying to spread the oil out so much that it maybe doesn't even reach this sort of state, or if it does, it's already dispersed. If the subsea dispersant addition doesn't cause that to happen or is not being done, and we do have surface licks, then we have the option of spraying dispersant on the free surface from an airplane, which is the more traditional way that dispersants have been used historically before Deepwater Horizon. And when you do that, you are changing the interfacial tension of the oil, trying to get it to break up out of the slick, and so that the available mixing energy of the wind and the waves can push it down below the free surface. By doing that, we are trying to remove the potential for human contact with the oil. People are most likely going to contact the oil at the coastlines and the surface, less likely are going to contact the oil in the subsurface. So dispersants are designed to try to move the oil away from human exposure and put it into the subsurface. And also these slicks are more easily transported to the coast, and so by suspending the oil subsurface, we try to reduce shoreline impact of the oil. The evaporation, though, is going to be removing a lot of the light hydrocarbons. So there's a window over time that dispersant addition would work. There's also a window of time where the oil can be collected by mechanical collection by surface skimmers, because this evaporation is rapidly taking out all the light parts of the oil, making the oil much heavier and stickier and more difficult to deal with. So this process of evaporation changing the viscosity and chemical properties of the oil is called weathering. We usually call it weathering because it's happening in response to the wind. And as the oil weathers, it becomes more and more prone to emulsification. So once the oil makes it to the surface, you have a short time to try to collect it or disperse it. After that, it will start to have enough evaporation that emulsification and weathering will take place. You'll get more thicker oils that are much more difficult to deal with. But those are the processes happening at the free surface. And this is kind of a picture of what I've been trying to describe as far as the subsurface. So I'll let you pause here and look at this if you want to see more details. Here's just an example of what I was trying to say with photodegradation, that not all compounds in the oil are affected by photodegradation. This gives an example of the molecular, so the amount of UV radiation that's going to be absorbed by, in red, a total oil, Hoops oil, and in blue, one particular compound of the oil, anthracene. And so we see that anthracene may be much more affected by UV radiation than the oil itself. And the anthracene is going to be converted into other compounds, and that is called transformation. And the rate at which that happens is going to depend on the amount of solar radiation reaching the oil, that can have typical half-lives of 0.6 to 2 days, which is similar to the biodegradation half-lives of light hydrocarbons. So photodegradation can be a very important process for transforming the oil, removing certain compounds like anthracene, but there is not a lot that is known about what these rate constants are and what particular parts of the oil are going to be degraded into what other compounds. The last thing to discuss is what happens at the sediment water interface. We saw during Deepwater Horizon we might form a subsurface intrusion. It formed at about 1,200 meters during Deepwater Horizon. It contains mostly dissolved hydrocarbons, but especially with subsurface dispersant addition, it may contain some very small oil droplets, especially in a future spill scenario where we may be engineering the dispersant addition to create more small droplets. These droplets and dissolved oil then are transported by the natural ocean current through the deep ocean, and if they then reach a continental rise or slope, then there's going to be interaction. So here we're seeing a subsurface intrusion directly impinging on the slope. The blue is supposed to indicate the dissolved hydrocarbons, and the black dots are very small oil droplets that don't have a high enough rise velocity to have gone much higher than this layer by the time it reaches the sediment. And so this can then just flow directly into the sediment if that's the flow field that's occurring at this location. It can transport then dissolved hydrocarbons into the sediments, and it can transport small oil droplets that will probably be filtered and accumulated by the topsoil of the sediments. At the same time, some of the oil that went to the free surface may have undergone different processes such as weathering or interaction with marine snow and phytoplankton blooms at the free surface. Under whatever process it may have been, formed a aggregate that has a higher density than water and started to settle. So maybe an oil droplet sticking to a marine snow particle. So these particles may be raining down on the seabed, and they would be covering the seabed wherever they have formed. They rain down in what we call a type of marine snow. Here I'm coincidentally showing them impacting the seafloor at the same location as this subsurface intrusion, but those particles could be coming down somewhere else. But we need to remember that for them to come down and impact the seafloor, they have to have a density greater than seawater so that they will sink. Light oils like Deepwater Horizon, it's nearly impossible to weather that oil itself to the point that that the oil itself would become more dense than seawater. But burning can produce burn byproducts that might be heavier than seawater. And again, as the oil rises, if it impacts on, say, the shell of a organism that has died and is now falling to the sea floor, that shell could have the density of silicon, which is about twice the density of water. When you hit it with an oil droplet, that oil mineral aggregate could still have a density that's greater than seawater and will fall to the seafloor. And there's a lot of research being done now about how that process might have been occurring during Deepwater Horizon. And you can Google MOSSA, M-O-S-S-F-A, as a group of, that's a consortium name. Don't remember exactly the acronym, but they are talking about this process, and they have a website and workshops. So this gives you kind of an overview of all of these processes we've talked about. Oil droplets in the water column degrade by biodegradation. They could go to the surface. Once they get to the surface, they could be re-entrained by turbulence at the surface, become droplets again. They can biodegrade and dissolve. They might form emulsions, which give you these kind of mousse and tar balls, larger oil-water mixtures that are harder to break up. There could be surface slicks that are letting oil compounds into the atmosphere. We can spray them with dispersant from a plane, trying to promote them be re-entrained into the water column, or we could try to collect them with a skimming vessel. The wind and the waves are going to be trying to, depending on their magnitude, trying to work the oil back down into the water column. And then the oil that does get dissolved into the water column is going to undergo a whole cycling process where the toxicity could be involved, and there are other modules that discuss how these compounds then become toxic. If the oil becomes heavy enough or the dissolved compounds move into the seafloor, then we might have processes going on in the sediments. So as a summary of this presentation, we've discussed that oil itself is a very complex mixture, that fate processes such as dissolution and biodegradation change the mixture composition, which then changes the properties of the oil, and so we have to have a model for the oil that can predict properties as a function of composition, and models that can predict how the composition changes over time. At the leak source, the oil is going to break up into droplets and bubbles, and these sizes are going to depend on the amount of energy and the property of the oil in terms of viscosity and interfacial tension. Deepwater Horizon came out of a broken riser, a future blowout could be bubbling up through the seafloor if the failure happens below the seafloor, or say if a tanker crashes into a rock and starts spilling oil from its contents, then you would have a much different size distribution than we had here in Deepwater Horizon. But again, it would be the energy of the discharge trying to break it up and the properties of the oil trying to hold it together that are going to evolve into a certain size distribution. In deepwater blowouts, if you can get droplets smaller than 100 microns, they will mostly stay suspended in the water column and biodegrade and dissolve before they reach the free surface. Larger droplets are going to reach the free surface and have fade processes at the surface. If they surface close enough together, they'll form slicks. If they're spread out over a big enough area, they may just be individual droplets. And we apply dispersants both at the source and from airplanes to try to break the droplets up into smaller droplets by reducing their interfacial tension, which helps them to stay suspended in the water column, either by turbulence at the free surface or turbulence at the discharge. Whatever droplets we get are going to lose mass by dissolving into the water and by being decomposed by the bacterial community in the water column. So the key processes happening in the water column as these droplets rise is that any dissolved gas might be coming out either as a gas bubble or through dissolution. The gas and lighter hydrocarbons are going to be dissolving. The longer chain hydrocarbons are going to be pretty recalcitrant to dissolution because they don't dissolve very much. But the density of that oil is going to change as the light things come out. And then the oil surface may be colonized by bacteria that will start to degrade the longer hydrocarbons and the short ones as well. And the bacteria work heavily on all of the dissolved hydrocarbons in the water column. Key surface processes are that we may form slicks. They will have different thicknesses. They will spread based on different wind and wave characteristics and the properties of the oil. If we have enough energy at the free surface, we can entrain the oil into small droplets that will stay suspended near the upper ocean. If we don't have enough energy, then they'll form slicks that are evaporating into the atmosphere. This evaporation is going to change the properties of the oil and eventually promote emulsification and formation of thicker oil mats if it doesn't get broken up and degraded before that occurs. Photodegradation through sunlight is also a new process that is not really happening in the deep water column, but does start to degrade the oil in the surface ocean. Key processes in the sediments are going to be biodegradation of the dissolved hydrocarbons, biodegradation of any liquid oil droplets, and the occurrence of liquid oil droplets either through sedimentation of heavy oil mineral aggregates or the transport of very small liquid droplets with the subsurface intrusions. Once the oil gets into the solid phase of the bottom, then it may start to partition between the water, the solid phase, and the oil itself. So I have several references. I'll leave this slide here. You can pause to read these and additional references here. If you have questions, you're welcome to email me at my last name minus KY, so SOCOLOFS @ TAMU.edu. Thank you very much.